Yep. All right, I'll take that as a collective no. No questions from homework or anything? No. You're good. Okay. All right. That was exciting. All right, guys. So last time we did the first part of section 4.2. So what we did was, let's do a real quick little problem here. Oh, let's see what we got there. 891, so I think it's 09. All right, guys. If I ask you, is this a valid probability distribution? You don't say, yeah, you made it, looks good. What's got to be true about these? There's actually two things. They got to add to be 1, and the other thing is kind of strange to say, but what's got to be true about probabilities no matter what? Any specific probability has to be at most 1 and at least 0. So do they add up to be 1? Somebody double check me. See if it's how rough of a day it's been. Yeah. Okay, good. Thank God. So they do add up to be 1. So the sum of the probabilities is 1. Check. And of course, each of these is between 0 and 1. Check. Because real quick, just to be silly, I could have something like this. Do they add up to be 1? Yeah. But it don't make a damn bit of sense. It's not a valid probability distribution. It's not a 150% chance it's going to be 0. Doesn't make any sense. All right, like maybe. How do I get the mean if it's given to me like this? This is what we focused on last time. How do I get the mean? What do I do here to get the average? To get the mean? Yes, good. I do the weight times the value. I can't just add these up and divide by 4. Where should the average be close to? What's the most occurring data point? Which data point occurs the most? 6. Because it shows up what percentage of the time? 72%. So if this is me asking people, at what age did you, I don't know, first take a ski lesson, just to go, or take a tennis lesson maybe. I see these little kids out there. I'm like, if only I would have started when I was 5. Then it looks like the most respondents said 6, right? There were 72% of people said they were 6 years old when they started taking tennis lessons. You guys with me? So the average should be close to this. Right, this may be pull up a little bit, but this also below that, it's going to pull it down a little bit. So maybe it's going to come out really close to 6. So 10.5% were 5s. So I multiply those. I multiply the weight times that. And I showed you the reason why. I showed you the math last time, why the math works out. So what is 0.105 times 5? That's right. I like it. And then 6 times 0.72. I like it. 8 times 0.085. And then 11 times 0.09. Yeah, cool. That makes sense. All right, how are we doing? The calculations are simple. But statistics is all about understanding why things work the way they do. So last time I showed you the math behind why this works. Because remember, what does this sort of mean? What can I look at this as? There are 105 fives. Yes?
4.32.
Oh, yeah, okay, that makes more sense. 4.32. Thank you. There, you can look at this like there's 105 fives, there's 72 sixes, 720 sixes, bam. 85 eights, 90 11s. I don't want to do that, though. I don't want to make that list of data and calculate it. So we created this quicker way to do the average. It actually is doing exactly what we did before. If you were here last time, hopefully that makes sense. It is doing the exact same work. I just have so many repeats that there's a quicker way to do it. So if I add these, that would be the sum of x p of x. Bless you. Now it'll come out right with a 4 in there.
6.5.
6.515, yeah. Sounds about right. I like it. Sweet. So don't just add these up and divide by 4, because there's a lot more than just 4 data points. Okay, cool. I like it. I like it. Now, 2 things. So this is the formula for the mean. And another name for the mean, hopefully this kind of makes sense. Another name for the mean is the expected value, because it's the value that you would expect. Does that make sense? So we're going to learn, well, we'll get there. There's a really nice example, but I can't quite do it yet. So we need to figure out how to get this standard deviation. So normally what I do to find the mean is I would add these up and divide by how many there are. But what did we do instead? We multiplied these by the weight of each. So what would I normally do to calculate the sigma, the population standard deviation? I would normally do x minus the mean squared and then divide by how many there are, right? But just like the mean, I'm not going to do that. I'm going to multiply each of those distances squared by the probability, by the weight. The exact same thing we did to find the mean. So I'm going to multiply those by p of x. All right, now, you could do that. All right, let me stop there for a second. Let's analyze this. So normally we would do this and then divide by n, right, to figure out the variance. Sum these up. It has been a long day. Get in there. All right, let me stop there. Does that look familiar? Does that look familiar? Okay. All right. I'll say to you guys, I'm not going to answer any of your damn questions. All right. And normally the mean would be sum of x over n. But now the mean is sum of x times p of x. And why does that make sense? What's on the bottom of a probability? What's always on the bottom of the probability? The total number. So what do I normally divide by to get the mean? The total number. But what's on the bottom of this? The total number. There's like a built-in over n. You guys, the p of x has the over n in it. So the formula is actually not even different. It's the same formula, it just looks different, so I can do it very quickly when I'm given data like this. So when I get data in different formats, I want to change my formula a little bit so it's quicker to get the answer. Maybe, maybe not. I love the idea that p of x, what's always on the bottom of it? N, the total number. So I'm supposed to divide the sum of x by n. Well, I did, because p of x has an over n in it. So instead of doing this, now I'm going to do times p of x. Same idea. The over n is built into it. All right.
That's to find the standard deviation?
That's to find the standard deviation. Well, the variance, right? That's the variance, because I haven't taken a square root yet. But it's already enough stuff there. I didn't want to put the square root in there, too. So I haven't square rooted that yet, but that's the formula. That's the way we used to do it, and this is actually the exact same thing. It just has a p of x built in because now they're giving me p of x's as part of my data. I want to build that into my formula so I can use it. All right, maybe. I love how some of you guys look at me so concerned, but then you go like this. Keep going. All right. All right. If you're cool with this, well, let me start. If you're not cool with this, that's bad. Okay, that's bad. If you're cool with this, then you have to be cool with this because the over n is here. It's the same damn formula. I just rearranged it a bit to make it so I can use that directly. Yes?
What do you mean by over it? I don't understand.
What is on the bottom of any probability? The total number, right? So what I'm supposed to divide this by n, but that is that's in here. The over n is built into this. Maybe. I love that idea. Ooh, some of you like, oh, I'm getting some. All right, I'm going to stop looking at you. All right, so I'll tell you this. This would be horrendous. That's the way the book does it, but I'm going to show you a better way. I love that. I love you guys so much. I'm going to show you another way, and then you can do either way you want to, okay? Some of you guys are like, yeah, your better way, whatever. Mathfully, shut up. All right, so I'm going to show you another way. And just like with histograms, you can do either way you want to. I don't care. All right. So let me take this away. I want to do this other some easier data just to look at. But first off, looking at this, just go with me here for a second. You're never going to have to do this ever. I just want to show you where this alternate version of this formula comes from. And then I'll show you how to do it in your calculator nice and quick. All right. It's going to be using the lists again. Of course it will, right? Kind of makes sense. All right. I'm just going to do the first couple steps because you could have an entire semester of summation algebra. I'm not going to make this class into that. You guys kind of follow. There's a whole way of working with this. But help me out. Bring out your algebra. Bring out your algebra. Bam. What would you do with this kind of thing in algebra? You can do it. You can do it. Don't freak out.
Multiply itself twice.
Yeah, you'd square it, right? You'd FOIL that bad boy out, wouldn't you? Please, dear God. Already some of you guys have tuned out, but for those of you still watching, you're just going to watch it happen. You're not going to do this. You should be able to, though. All right. Mu x, so minus 2 mu x plus mu squared. Now watch. The first, if you distribute this now, do you see that? This is like the last step I'm doing, so don't freak out. Because the rest of it involves quite a bit of manipulation of stuff. Because remember, what is mu? Sum of x over n, right? And so forth and so on. Oh my God. So you can do a lot. But I just want to show you at least where the first part of this comes from. X squared times p of x, right? Is that cool? That's the first term I get. Is that cool?
Oh.
And now, the part that I'm not going to go through. If you want to see, you can come to my office or whatever. I might make it an extra credit problem. You never know. But everything else, you convert that to sum of x over n, and you put it all together, and you combine like terms, it becomes that. It's crazy. So this is the alternate version for the variance. And the beautiful thing about this, so let's do an example problem. If you want to do it with the other formula, you got examples in the book already. So I'll let you look at those. So let's do an example, list of data. And then I've got, you know me, I've got my little handout with the full example, and then the other side is going to be you guys doing a problem here in a minute. Let's do one here together. If you wrote some of that down, you're crazy. You didn't have to. You don't have to look at that ever again. But that's the formula I'm going to use. Oh, yes. No, I just write every damn thing down you put up. All right. So let's do some nice, decent, not too crazy data. Let's play. Now let's make the probabilities kind of nice to work with. All right. So thankfully, the sum of the probabilities is 1. All right. I'll let you guys write that down. We'll do this on the board by hand, and then I'll show you how to do it in the calculator. The numbers are nice enough we can do it up here. I have to make the next column to be what? Considering that the formula for the mean... Oh, and by the way, I forgot. The other name for this was what? What was the other name for the average? Expected value. And look at the first 3 letters in there. Oh, holy shit. So if I ask you to find the expected value, you look at your formula sheet, EXP, that's the first 3 letters. It's crazy. It's crazy. If you let it happen, the formula sheet is notes. They do be notes. So I need a column, of course, of what? We just did this a minute ago. I got to make what? XP of X, so I can add them up and find the mean. So 2 times 24? What? No, yeah, I know. I didn't think it was an answer. I believe that would be a 2. What about 4 times 0.3, 1.2, 5 times 0.2, 1? So then the mean is the sum of XP of X, which is 3.3. Let me stop there for a second. So that's old news by now, believe it or not. Even if you missed last time, that's old news because we just did one earlier. Does it make sense? 3.3. The average, if it was just these, would be 3.5. Why is it less than that? Because do you guys see that? Normally it would be 3.5 if it was just 4 data points, but it's not. It's this. What's the heaviest weighted data point? 2. So it's going to pull the mean down a little bit. So it's not 3.5, it's 3.3. That makes sense. I like it. I like it. All right, so the beautiful thing about this formula is, I don't know if you guys realize, I already have an x times p of x. What does that formula require me to sum up? X squared p of x. So all I got to do is multiply these 2 columns. And I get x squared p of x. So, oh my god. You alright? What happened? Help me out. What is x times x p of x?
X squared p of x.
And isn't that what that needs?
Yeah.
Okay, so if I take the x's and I multiply by the x p of x's, I get a bunch of x squared p of x's. And that's what the formula requires me to have so I can add them up. I like it. I like it. So here are my new, well, let's see, this isn't too bad. 2 times 0.8, 1.6, 3 times 0.3, 0.9. Yes, ma'am?
I'm just wondering, where are you getting the p of x from? Is that going to be given to
this
us?
has to be given.
Oh,
Together, this makes a list of data. So, it's, for example, what could the list be? It could be, have we not done this enough yet? It could be 4 2s and 1 3 and it could be that, or it could be double all of that so that the ratios still come out. So they have to give me, if they didn't give me a whole list of data, they said the first 2 data points are 2 and 7. And then there are 11 more data points, find the mean. You're like, who the freaking hell are you? So they have to give me all the data, so they have to give me both of these columns. I have to be given those. I like it. Because that's giving me the whole list of data. So 4 times 1.2? 4.8. 5 times 1? 5. And now if I add those up, this is where you got to be careful. If I add them up, I get the sum of x squared p of x, and that's just a part of the equation, right? You got to throw that number into the equation. So what do you get when you add those up? 12.3? Yeah. So then the variance will be the sum of x squared p of x, bless you, which is 12.3, minus the mean squared, and the mean was 3.3. Just plug stuff into the equation, like we've done before, and you get something. What do you guys get when you do that? 1.4? 1 blah blah blah, and then take a square root, right? Or did you already take a square root? You already? Because that's the variance, right? It's got a little square on it, which means it wants to be taken a square root of. So you should get 1 point. Yep, 187. I like it. All right, let me stop there for a second. So we've already determined that with the center and with the measure of how much the data gets away from the center, those two numbers summarize my data really well. So every time I come up against a new way to give data or to find data, I have to come up with a new way to find the mean and the standard deviation, or at least a new formulation of that. A new way to make it look. Maybe. So, let me show you guys how to do this on the calculator. Possibly. Yay! Maybe. Why is it frozen there? What is happening? Poor little dude. Oh, there it is. Okay, good. God, this room is stuck in the 50s. You put new technology, it freaks out. Okay. Woohoo! All right. So if you have your calculator with you, if you want to borrow one, I still have the bag up here. But you can just watch. And I got these instructions on this handout I'm going to give you in a minute. Rah. Okay. Oh, shit, it's still... Come on. Please. Please do what it says to do. This is the weirdest thing. I don't know what's wrong with the little dude. Somehow it's frozen. Where's the... Somebody freeze something or something? No? Oh well. It's the weirdest thing in the world. Oh, too bad for us. It won't show it's actually on the screen. It just wants to show, it just likes, there's my mouse.
Yeah. I think it thinks like a second monitor is going to track like to the left.
Oh.
Yeah.
Holy shit. Okay. Neat. So why? Alright.
I don't know why. It's not.
Now I can't see it. Alright, here we go. This will be exciting. Alright, let me make this thing small again. Let's see.
Oh my god.
That's too fun. So it must be in 1 second. Or maybe 7. Oh, yeah, John. Yeah, you did a good job. I decided the problem wasn't bad enough yet. All right, Lord, come back. Oh, now I'm screwed. All right. Oh, that's so weird. It thinks that that is the second display. It thinks that that's the second monitor.
Yeah.
All right. Holy shit. All right, you're reverted. All right, that's probably for the best. All right, guys, I'm sorry. Hold on. I'll just do this one, and at least I'll be able to see what's going on if it'll do it. Will it do it? It did it. Yay! Keep the changes. Go away. I'm going to hunt down whoever else is in this room and say, what the freaking hell? All right. So if I go to my data, my lists, where I can input data, you're going to have to obviously use the first two lists, right? To put the x's and the p of x's. So let's just kind of, let's recapture this. So 2, 3, 4, 5, 0.4, 0.1, 0.3, 0.2. L3, clear it. L3 I want it to be what? I want it to be x times p of x. Well, the x's are in, where are the x's up there? L1. Where are the p of x's? L2. So I want L3 to be L1 times L2. That's x times p of x. And I get my 0.8, 0.3, 1.21, the numbers we already got. And then if you go over to L4, you want that to be, let's see if you guys remember, how to get the fourth column.
L1 times L2.
L1 times L3. You could do L1 squared times L2. Do you guys see how that would still be x squared p of x? Either way you do it, it's going to be x squared p of x. But I'm just going to do L1 times L3. That's x squared p of x. And I get my 1.6, 0.9, 4.85.
Can you just quickly repeat what L2 is?
So L2 is given. L2 is the p of x's. L3 is x times p of x. So it'll be L1 times L2. And I've got this on the handout too. So I'll give that to you here. Yeah. Right? And then L4 is L1 times L3. Okay. So let me do this. And then you can sum them up the same way we did before. Right? So let me give you this. On one side is an example, fully worked out. The other side is the one I want you to work on right now. Cool. It's over here. I've lost you.